Find the general solution to the differential equation y double prime minus 2y prime plus y equals t to the negative first e to the power of t. So we're going to use variation of parameters. You could also use Laplace, but in this case the problem asks to use variation of parameters. So as always, we need to start off with the homogeneous portion, in which we set the left-hand side equal to 0. And we form our auxiliary or characteristic equation, where we take the power of r equal to the amount of derivatives being taken on y. So r squared for y double prime minus 2r for 1 prime, and then just plus 1 equals 0. So factoring this out and solving for r, you have r minus 1 times r minus 1. Since negative 1 times negative 1 is positive 1, and minus 1 is negative 2, equals 0. So we have a repeated root where r1 equals positive 1, and r2 equals positive 1 as well. This is important for our homogeneous solution, such that it equals c1 e to the t, since the coefficient of t would just be 1, plus c2 times t, since it's repeated, e to the t once more. And that is our solution. Now, for our particular solution, we have to focus on e to the t and te to the t, where we call those functions y1 and y2, which are needed since y particular, using variation of parameters, is v1 y1 plus v2 y2. And we will be using Wronskian approach, where v1 equals negative integral of y2 f of t over Wronskian, and we call f of t everything that's on the right-hand side. On the other hand, v2 equals the integral of y sub 1 f of t over Wronskian. Now from linear algebra, I'll do it over here. Wronskian is just to find linear independence of two functions, y1 and y2, where we need their respective derivatives. So the determinant would thus equal y1 y2 prime minus y1 prime y2. Now we can see here that we said y1 equals e to the t and y2 equals t e to the t. So to find Wronskian, we need to get their derivatives. So y1 prime is still e to the t, and y2 prime using product rule, where it's f prime g plus fg prime, where we call t f and e to the t g. So derivative of t with respect to t is 1, g, plus t times derivative of g, e to the t, is still e to the t. So it's e to the t plus t e to the t. Therefore, Wronskian equals y1 e to the t, y2 prime e to the t plus t e to the t, minus y1 prime e to the t times y2 t e to the t. Does anything cancel here? Let's check. So this would be e to the 2t when you distribute this, plus t e to the 2t, minus t e to the 2t. And yes, something does cancel. So we're left with Wronskian equaling e to the 2t. So now we can find v1 and v2, and ultimately our particular solution. So v1 equals negative integral of y2, which we said was t e to the t, times f of t, t to the negative 1 e to the t, over Wronskian e to the 2t. This may look like a complicated integral, but let's see if we can cancel anything. So you can see e to the t on the numerator times e to the t is e to the 2t, and for us that can actually cancel the denominator e to the 2t. And also when you look at that, t times t to the negative 1 are just inverses of each other, so they cancel to be 1. So we're left with negative integral of 1 dt, or just dt. And with respect to t, that's just negative t. So v1 equals negative t. Now for v2, that equals integral of y1 e to the t times the same t to the negative 1 e to the t over e to the 2t dt. Same thing here, the e to the t's cancel everything, and we're left with the integral of 1 over t dt. And as you know, that's ln absolute value of t, which is our v2. Now we can find our y particular. v1 we said was negative t, y1 we said was e to the t, plus v2 ln t, y2 t e to the t. And nothing cancels here, so let's just rewrite that. I'll rearrange it so that we have ln in the first term. And there you go. As we know, for y general, that equals y homogeneous plus y particular. And from up here, I'll start that. We have y homogeneous equal to c1 e to the t plus c2 times t e to the t. And all we have to do is now add our y particular and we're done. You could circle this as your answer, but there is one extra simplification you can do. As you can see, there is a repeated term here. We call this c2t e to the t, and some constant t e to the t, where that constant is -1. Therefore, in this case, you can call c2 equal to -1 here. So technically, that's just restating yourself. You're saying, for instance, oh, there are all even solutions, as well as 2. Like, technically that's correct, but it's better to just say all even solutions. So you can actually cross this out because you're reiterating the answer. So you can simplify this one extra step and just call it c1 e to the t plus c2t e to the t plus t e to the t ln absolute value of t. And that also is a valid solution. And again, the c2 term is encompassing the -1 t e to the t term as well. So, I hope that made sense. If it did, please like and subscribe, and I'll see you in the next video.